going to learn something today. Now let me give you a breakdown of what we're going to talk about here. We're going to talk about what machine learning is. We're going to go through a few different models, and what a model is basically an algorithm for machine learning. And for each model, we're going to talk about the theory behind it, essentially how it works. We're going to talk about some of the strengths and weaknesses for each model. And then finally, we're going to talk about the application of it via examples and maybe a few other things as well. All right, let's get into it. What is machine learning? Now, the formal definition is something like a field of study that gives computers the ability to learn without being explicitly programmed. But you're probably not going to remember that definition. And what I really want you to remember is this: using data instead of logic to predict or classify new data, or even just using data instead of logic. That's the fundamental idea behind machine learning. And what I mean when I say that is something like this. Telling a computer 1 and 2 is 3 versus telling it to add 1 and 2 explicitly. And this is sort of a toy example, and we'll get into another toy example that's sort of more real world. But yeah, and how you would train a computer to learn to add is you give it examples of addition. You say 1 and 3 equals 4. You say 3 and 7 equals 10. 5 and 6 equals 11, and so on. And then, without knowing that it's doing that, it would learn to add, essentially. Now, a more real-world example is something like a fraudulent transaction for banking. And sort of the old generation, or for some banks, the current generation, is a logical approach, where you say, if the transaction is over $200, and if the transaction is over 500 miles from the last transaction, and there's never been a transaction within 100 miles of where the transaction is, then flag the transaction as fraudulent, freeze the account. A lot of us have sort of been the victims of that logical approach, where the machine learning approach would be this: you would give a model examples of both fraudulent and non-fraudulent transactions, and you give them the data related to those transactions, and then for each time you would tell it whether it was fraudulent or not fraudulent. It would learn the patterns that represent a not fraudulent and fraudulent transaction. Now let's get into our models. First one's linear regression, KNearest Neighbors, support vector machine, and neural networks. We're going to go deeper into all of these, but you'll notice that I say supervised machine learning models, and we'll get into what that means a little bit later, but just something to keep in mind. Linear regression, most of you are probably pretty familiar with what this is. Line of best fit, y equals mx plus b. You remember that from algebra. Essentially, it attempts to predict a value based on data, and you can calculate the slope of your line of best fit very easily as sum of squares y over sum of squares x, and basically all that is the sum of the difference for each point's distance from the y-mean over the sum of the distances from the x-mean. So it's basically the sum of rise over run deltas, essentially. It's very simple, and that's the equation for that. And then you find the y-intercept simply by the knowledge that any line of best fit has to pass through both the y-mean and the x-mean. So that's an existing point we have. We have y and x by the x-mean and y-mean, and we have our slope now from calculating that equation. Now you just solve for b. Anyway, the accuracy, how you judge the accuracy is for every point you find your r squared, which is the sum of the distances for every point from the actual point in the prediction. From here it'd be 0.5 squared, for this it'd be 1 squared, for this would be 1 squared, and so on. And then it's the ratio between that sum and the sum of squared y, which again is the sum of the differences between the points and the y-mean. Let's say it's somewhere over here. So for this first point, you can see the ratio between the predictions distance and the means difference is pretty far, and so your accuracy would be pretty high. Let's say your model was just as good as your mean at predicting a point, then your accuracy would be 0, because this ratio would be 1. It'd be 1 minus 1 equals 0. And in this case, a 1 would be 100% accuracy. And the great thing about this model is that it can be scaled very easily. It is very inexpensive computationally, and yeah, it's just fast, which is, and even though it's so simple, it can be useful. And we're going to get back to how even the more complex models sort of mimic this. All right, next model. K-nearest neighbors. Now this is a classification model. Linear regression is a prediction model. And the difference between a prediction model and a classification model is basically the difference between a continuous variable and a discrete variable, an integer and a double for you guys. Like essentially, for classification, you would say that a point is either red, blue, or green, whereas for prediction, you would say it is 1.357 on the color spectrum. Anyway, so how this model works is you take all of your existing points, and for a new point, a new piece of data that you're trying to predict the class of, or classify rather, you find k nearest neighbors. You calculate the Euclidean distance for all the points, and you find the nearest neighbors, and it's basically a voting system. For this one, you can see it has 4 nearest points that are red and 1 that's green. Therefore, you classify that point as a red. Very simple. And the great thing about this is that you essentially don't even have to build a model. You just take your existing data, and that is your model. However, one issue with this algorithm is that to predict to classify a new point, it actually kind of takes a while, especially if you have millions of records, because, as we all are probably familiar with from school, calculating the Euclidean distance from every single point in a data set can kind of take a while. All right. And also, the accuracy for this is calculated a little bit differently than linear regression, but pretty much linear regression is a little bit unique in that you can use all the points to calculate the accuracy, whereas for this model and every other model, you have to split up your data. You have to shuffle your data and then split it up into a training and testing set. And usually it's about 80% training, 20% test is the typical ratio, kind of like the standard for it. So you take your training set, your 80%, and you plot those, or you just create your model with it, and then you take those 20, and you attempt to classify them. When it classifies it correct, you know, it's good. When it's not, and basically the accuracy is the ratio between total testing points and the number that you get right. Pretty simple. All right, support vector machine. Now this is a powerful model, and this, until recently, was the go-to model. And the reason is because it can solve very complex problems. It's very computationally inexpensive compared to some of the more advanced neural network models. And it's also pretty straightforward and easy to implement most of the time. And what it is a binary classifier using hyperplanes. Now, what does a binary classifier mean? It means that it basically classifies something as one or the other. And it uses these hyperplanes to do it. And a hyperplane in 2 dimensions is a line, hyperplane in 3 dimensions is a plane, hyperplane in 4 more dimensions is the hyperplane. That's why it has that name. You can't really visualize it, but it's a flat surface, essentially. And you can see that this is our hyperplane. And these are the support vectors, and essentially the hyperplane is essentially the best plane, the best dividing line between the 2 classes, with the largest margins between the nearest neighbors of the existing classes. So here you can see there's no better line you could draw there that would further separate those 2 or create any larger margin between the nearest points from that line. And there's basically a 1 versus rest and a 1 versus 1 sort of version of this model. And essentially what that is imagine there's another class right here, green points, and it's just bang, 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 right there. 1 versus 1, your blue would have one hyperplane separating it from the yellow, and then it would have another hyperplane separating it from the green, let's say like right there. Whereas 1 versus rest, your hyperplane for blue would just be one hyperplane that separates it from the rest of your classes. I hope that makes sense. Okay. Now there's also this C parameter, and the C parameter is essentially how much does it take outliers into account or not. So this is very pretty data, as you can see. If all the 2 classes are like perfectly separated. Real data isn't like that. Real data, you have a yellow point that's like inside this blue. And if you had a high C parameter, that kind of means strictly split this data up. And what that means is that your hyperplane would be right on where this existing support vector is. And it would be right there, and you have no margins between your blue and your yellow. However, if you specify a low C parameter, what that's going to do is it's going to ignore the sort of outlier yellow that we have there, and it's going to keep, generally speaking, this same hyperplane to better generalize a model. And when I say generalize, I mean take new data, accurately predict new data, not overfit to the existing points. And the reason that this is so powerful, we haven't really talked about anything that gives it the power quite yet. But what it is the kernel trick. And what the kernel trick is you apply a function to your existing data, you add a dimension, and then via adding that dimension, you make your data linearly separable. Because your data has to be linearly separable. You know, imagine if there are blue points over here and yellow points over here. You can't just draw a line between them. Anyway, so right here is an example of this. So I don't know if you guys can see this, but all these inside points are blue, and all these outside points are red. And so you can't just draw a line through there. You can't put a hyperplane through there without applying a kernel. And the kernel in this case, I'm just going to guess, is something like x squared plus y squared equals z. And now that you applied and added a dimension, now you can see your data is clearly linearly separable. You know, z equals 0.6. That puts a hyperplane right through that data. And now you have a fairly good classification system for data that was previously not linearly separable. And this, just so you know, like again, I said this is our most powerful model until recently. Like this model, via this kernel trick, can do things like classify a handwritten digit and things like that. Like pretty advanced task this can accomplish. It's only until recently that neural networks have sort of surpassed it in ability, gotten those last few % error off of the accuracy. All right, now everything we've talked about has been supervised machine learning. And what I meant by that is that for every classification system, we've known what our classes are. We've had our class and label is synonymous in machine learning or in data analysis. So basically what unsupervised machine learning does is it clusters unlabeled data. So whip out the whiteboard. Imagine we had, here's our x and y axis, imagine we had a cluster of points here, and we had another cluster of points here. But we didn't say that these are dogs and these are cats, because it has no way of knowing that. You use a unsupervised machine learning clustering algorithm or model to find those two groups, essentially. And there's two different types of clustering. There's flat and hierarchical, or however you say that. And basically flat, you tell it, find me two groups. Hierarchical, you say, find me your best guess of the number of groups and what the groups are, essentially. And there's no evaluation of accuracy for this because we don't know what the actual labels are. So essentially, you just tell it to run, and it gives you back what it gives you back. And you can try and test how well the model does by giving it data that you do know the labels of, but you don't give it the labels. But yeah, there's no real reason to do that except for to test it with. But and also you can do things like semi-supervised learning, which is you take unsupervised machine learning, you get your clusters, and then you apply supervised machine learning to that, now knowing your clusters, and you can create models to classify new data into one of those clusters, essentially. Now, any questions? I'm seeing a lot of like blank faces. I encourage you guys to ask. We've been moving pretty quick. No? Okay. All right. Well, what we're going to do now is we're going to go into some useful tools, and then I'm going to show you some examples of how powerful Python is and how easily you can implement these models that I just went over. Now, NumPy is these are all libraries in Python. NumPy basically has scientific functions, matrix and vector multiplication, really handy for doing machine learning. Pandas, basically it easily allows you to read in data from data files such as CSV, XLS, any type of normal file that you would think to read data in. It will have an easy way where you can just say read CSV, give me the file path. And also it puts them into data frames, which is essentially like a fancy matrix where instead of giving the index of the column, you can just say give me a height column, and it'll give you that. sklearn. Now I'm about to expose the power of sklearn in a second. And what it is, it basically has a bunch of pre-made machine learning models as well as tools to use for machine learning. And via this, you can implement all three of the machine learning models that I just mentioned extremely quickly and easily. And it is so powerful for implementing machine learning into an application where you may want to. It is so powerful. Pickling essentially just lets you save off an object into a pickle file, and then you can reload it back. And it basically allows you to not have to build the model every time you reload the program. Natural Learning Toolkit, essentially it just has a bunch of tools for text analysis. You can do things like stemming, where you take the tense off of words. You can do things like chunking, where you say, give me every adjective and noun pair. So it'll give you something like dark horse, or tall man, or I don't know, any sort of set. However, you create a regular expression for chunking, and essentially it will give you back sort of the types of parts of speech, or the chunks of parts of speech. Anyway, TensorFlow. Basically what that helps you do is create a neural network model, especially deep neural network models. It just makes it a little bit easier, especially for optimizing one. KNearest basically is large publicly available data sets. One of the reasons that neural networks have sort of come into their own is because now we have data sets that are large enough to actually train them, where they can generalize a model that's effective. All right, let's get into these coding examples. I'm going to show you coding examples of the first three, and I'm not sure if you guys will appreciate this, but I think this is pretty damn cool. Okay, so here's basically we're using pandas to read in our data. As I mentioned, we're replacing any null values with just an outlier value. We're dropping our ID column, because typically an ID is sort of irrelevant information. And first, let me give you some information on what we're going to do here. Basically, this data is cancer patient data, and what it has is it has your ID, the 1 to 10 rating of your clump thickness, your uniform cell size, just a bunch of different aspects. And then finally, it has your stage, which the column name is class, but your stage of cancer, stage 1, stage 2, stage 3, or stage 4. And what we're going to do is we're going to try and classify new data into, create a model that can classify someone as their stage of cancer. And this is real data. This is like actually, we're doing something here. That's essentially what I'm trying to say. So we drop our ID column, because that's pretty much pointless data. It's just going to confuse our model. And then we're separating our labels, or our features, from our labels. And what I mean is, let's say pictures of cats and dogs. Your feature would be your actual image, your features would be the actual pixels, and your label would be cat or dog. It's just the class of the data. So now we're pulling off the class, so now we just have the 1 through 10s in our X and our class in our Y. We use this cross-validation to shuffle our data and split it up into a training and testing set, and you can see I specified 0.2 here. What that means is an 80-20 split, kind of like I mentioned earlier. And here's where it gets cool, at least for me it does, is you can see all I say here is I create an instance of linear regression. I tell it to fit that data, and then we've created our model. We can test our accuracy just by calling the score method, and we can print it out, and let me run it for you. Here you can see our accuracy. We are 77% accurate at predicting a cancer patient's stage. And again, linear regression is a prediction model, so it's going to give us this continuous variable back. So it says 2.3 stage, so it maybe thinks you're like a little bit advanced stage 2. But here's all you have to do using sklearn, just change your model. It is a one-line change. It is freaking awesome. And these are using all default parameters. Like you'll notice I don't specify my K here. It tries to do its best guess at sort of defaulting a K here. But you can specify your parameters, and you can optimize your model essentially. That's all we have to do here. And now we run it again, and suddenly we go from 77% accuracy to 95% accuracy. And you can see here it classifies, it doesn't predict, it tells us this is stage 2 cancer. And also I pulled one of the records out of the data set, and that's what this is for this prediction, and that is correct, it is stage 2 cancer. So far this thing is pretty well classified a cancer patient, a real cancer patient. And then to switch to a support vector machine, all we have to do, again, one-line change. And again, we can specify the parameters. It has default parameters that are okay, and it gives us back 97%. Classifies it as a 2, classifies it correctly. And that is sort of the power of sklearn. And this is already up on SharePoint, and also the folder is shared directory advanced lunch and learns, Josh Medlin lunch and learn. You'll be able to find it. Just look in the events folder essentially under shared docs.
What variables did you say it was looking at when making the stage?
It is looking at your clump thickness, your uniform cell size, uniform cell shape, marginal adhesion, I don't know what that means, single epicell, and these are all 1 to 10 values of, I guess, how thick the clump is, and basically a 1 to 10 value for all these, I don't know what you would call this, all these conditions.
I'm not sure if you know this, it's fine if you don't. So if a doctor looks at all these things, they could plug this all into your machine learning algorithm and say, hey, this guy's probably at stage 2 or stage 3.
Exactly.
As opposed to doing what?
As opposed to guessing or trying to take it upon themselves to look through other examples of cancer patients and do their best to guess. I don't know how exactly you classify cancer, or your stage of cancer, but this would be a tool to get a good guess before you do further research, something like that. This is a real-life example of how you could apply this. But yeah, let's get back into our presentation. Oh shit, let's not do that.